Just pulling up some stuff here. All right. Okay. All right, so let's get started. So before we start the actual lecture for today, we'll go over a few things. Let's go to the page for today. Okay, I didn't add very much stuff on the schedule. So before we get started, let's see, your grades for the third memo, they're almost done. So, you know, I know, I always say this, but I wish I already had them up, but they will be up before your fifth memo is due. So your fifth memo, that's due on the 29th, I believe. Let's double check that. Yeah, the 29th, all right? And your fifth memo, you got to do that by yourself. So, I mean, you got to do the data reduction by yourself. So, hopefully you already saw the email for that. But if you didn't, you got to do that one by yourself. And I want you to kind of, you know, try to do that data reduction, you know, using your own kind of method. So try to do it, you know, whatever you think is best in the beginning. But if you get stuck, I did upload a kind of guide or a recommended, I don't know, attack plan, I guess, if you're kind of stuck. So let's go to that. So if you go to the deliverables, need to go. Okay, I was here. Okay, so if you're stuck and you can't figure out kind of what to do for the data reduction on the fifth lab, I did upload a kind of recommended guide or attack plan for it. But I want you to try to do it by yourself in the beginning because I don't want to box you into, you know, my method, right? You can solve this data reduction, or, you know, you can figure out what to do, you know, using a different method than what I used. So I want you to try to do it by yourself first, but if you're stuck, you can take a look at this guide that I have here and you can try to follow that. So for me personally, I use 2 for loops, nested for loops. So in my kind of outer loop here, I looped through for the 2 different data sheets that we have, so the 2 different kind of stations. And then in the inner loop, I'm looping through the 3 different materials that we have for each of those data sets. All right, and then basically what I did is I solved for that kind of transition energy that we have. So when we're transitioning from ductile to brittle, you solve for that, and then you kind of make a vector after that using the polyval function in MATLAB. And basically we want a vector so we can actually kind of plot a line. And then once we do that, we can plot that line with the impact energy versus the temperature curve, and then you plot both of those lines, and then you can find the intersection point between those 2 curves using the poly-x poly-y function down here, which we used in the very first lab. And once you plot both of those, use this function, you can find that intersection point, and then the x value for that's going to be the ductile to brittle transition temperature. All right. So basically, in the end, you should get these kind of graphs down here. So I think these graphs are actually, these graphs, they were from the data for this section, okay, if I remember correctly. So your graphs should look like this. Again, I'm pretty sure it was for this class. It might be for my 1130 class. I'm pretty sure it's this class, though. So your graph should look like this, and you should have a ductile to brittle transition temperature for 1018 steel and 4140 steel. All right, for the aluminum, you know, it's easy just to write your code where you also solve for a transition temperature for that as well. It's just convenient to have your code that way in your loop. But in reality, you only have a transition temperature for both of the steels. You don't have one for aluminum. Now, if you look at this aluminum graph for both of these, there's not a transition temperature for that. You know, there might be some issues with the data. So like on this data point over here, for this was for liquid nitrogen for this left station. It was a little higher than what it should be. But, you know, either way, there shouldn't be a transition temperature for aluminum. So just keep that in mind. And basically what I'll do in the end is I'm going to make sure from the code that you upload at the end of your report that you solved for this transition temperature in whatever method you want to use. But I'm going to check that you actually solved for it in your code. Okay, so I'm going to be looking out for that, and that's going to be how you get some of your points. So make sure that I actually can see that in your code. All right. So any questions on this? I mean, I'm not going to help you with the code right now, but are there any questions for the fifth memo? Nope. Okay. So yeah, so I'm gonna be looking out for that, and of course, again, your third memo, that's going to be graded. You know, probably this weekend I'll get the grades up for that, and I'll try to get your grades for the fourth memo up as well during the break. No promises there, but I'm gonna do my best to get those up too. And then you know, so like I was just saying, we do have a break next week. We have fall recess, so there's no class next week, but after that there's going to be class where we're going to have the sixth lab, so that'll be in person. That's on December 3rd. Okay, and then the week after that we're going to have a kind of review for the final, and that'll be online. Okay, so we're going to talk about what you should expect for the final. I'll kind of have a study guide as well. So that'll be a pretty fast class, to be honest. So we'll kind of talk about what you should expect on the final, what the format is going to be like, that kind of stuff. But I'm going to give you the study guide, and it's up to you to fill that out yourself. Okay, so let's talk about the sixth lab now. So I'm going to pull up the procedure here. I haven't uploaded this to Canvas quite yet, but we'll kind of get a little preview of what this last experiment's going to look like. So sixth lab is going to be the double shear lab. Okay, so this is our test setup here, using the MTS machine again, and we have different fixtures. Alright, so we're going to have 3 different materials, kind of like we do pretty often. So we have 60, 61, T6 aluminum over here on the left, and all of these are going to be color-coded, like usual to you, on the ends of each of these rods. So green is aluminum. Here, blue is 1018 steel, and then over here, this is copper, and that'll be colored red. Alright, so what you're going to do, you're going to record the diameter in 3 different spots like usual, and then we're going to put all those down here. We'll get the average diameter, and then after we run our test, we're going to take note of the length that we have on these columns at the end. So that'll make a little bit more sense once you see the test setup. But you're going to record the length after the test, and we're going to be using that length for the bearing stress calculation that we're going to calculate that as well. So this is the bottom fixture here. So we're going to have these 3 different discs that we need to put in this test setup. So these 2 here, they're going to go in these kind of slots right here. And then our centerpiece, well, obviously that's going to go in the center. And then through these holes that we have, we're gonna put the rod. So you can get a better idea how it looks here. And then we're gonna put the rod through there. Okay, you can kind of see, it looks like this is aluminum here. We have that through the holes here. And just like we did for the column lab, we're going to be using the thumb wheel on the hand controller to apply a very small preload of about 0.2 pounds. You know, so it says 0.2 pounds, you just want to be around there. If you're like 0.5 or something, that's obviously fine. Okay, we're going to zero everything out. And then we're going to run the test. So you're going to see you have this load versus crosshead graph that's going to show up. And what the crosshead means, if you guys don't know by now, so I've had some people ask me about that, what that is. It's basically the location of this top jaw here. So it's this top jaw. It's going to record how much, in this case, how much it's going down, how much it's moving down. Alright, so we're going to get this graph. So basically you're going to see that the load is going to increase. It's kind of similar for how this graph looks to the very first lab. I guess first lab. So we're increasing with the load, and eventually it's actually going to start to decrease because, you know, we're assuming that the area is constant, which is true actually for this lab. But basically the load will increase, and eventually it's going to kind of drop off here, and it's going to fail at this point. So so the load is going to suddenly just drop down, and this is when it's going to fail. And yeah, so it's not that interesting of a graph, to be honest, but basically what we're going to be doing in the end is we're going to look at this maximum load here. We're going to get that, and then we'll divide that by the cross-sectional area, and that's going to give us the shear strength that we have. So kind of like we have the ultimate tensile strength for the very first lab. You know, we're going to convert this load to the maximum shear strength for this lab. Okay, so we're going to be doing that. You're going to export your data, and this is what it's going to look like in the end. So it's going to shear in two different spots because it's a double shear lab. So we're shearing right here, and we're shearing over here. So this part kind of got a little stuck here. This one fell down. And then you're going to get the material that's in the center here, and you're going to take that out, and you're going to record that length. So kind of in the middle here, we have bearing stress, right? So we have the shared surface with the rod that's kind of in the middle here, with this kind of area, this area, and this area. We'll get a better view of that later on. But we're going to get that length, we're going to record that, and then we're going to use that to calculate the bearing stress. Okay, and then for each material, we're going to test it twice. I mean, so it's obviously sheared here, but we're going to take the kind of leftover material, and we're going to test that again to do this double shear test twice for each material. Just like for lab 5, I don't know if we did it in any other lab. We're going to take pictures of the material after it's sheared. So this is the very center of the material. We're going to take a picture. Oh, I didn't even notice. I just noticed this right now. I didn't know that you could adjust the brightness for the camera. That's useful. Alright, so we're going to take a picture of the fracture surface here. And you'll see for a more ductile material, it's going to smear quite a lot. So this looks like it's copper, so you see that it's smearing a lot, because, you know, as we're applying this shear force down, if it's a really ductile material, it's going to continue to it's not going to fracture right away. It's not going to fracture right away, so it's going to smear quite a lot. But if we have a more brittle material, it's not going to withstand that force as well. So it's not going to smear quite as much. Okay, so this is copper. So you'll see for copper, it's going to smear quite a lot. In fact, it even might look a little more smeared than this picture. Usually we see copper, it smears across this whole kind of cross-sectional, or this whole diameter here. So just keep that in mind. And yeah, so you're gonna record that length just like it says here, and you'll put that down on your Excel sheet. And again, we're gonna use that to be used for the bearing stress calculation. Okay, so that's what the lab is gonna look like. Okay, so now I'll pull up the my iPad. Yesterday it was kind of, the connection wasn't great from my iPad to my computer, so hopefully it's better today. Okay. So by the way, this is a pretty fast lecture. Alright, so I already wrote some stuff down, obviously, just to kind of get it out of the way. But again, we're doing the double shear lab for our very last lab. And so we have these 3 metal rods that we talked about. We have aluminum, copper, and 1018 steel. I think the copper that we have is C40. I'll double check that in the end, but yeah, I think that's what we have. So I'll tell you guys, obviously, once we're in the lab. I'll check the lab handout that we have from the department. Alright, so we have these 3 materials. We're going to subject them to double shear. So obviously not single shear, but double shear. We'll talk about that a bit as well. And we're going to, just like we do for a lot of labs, we're going to compare the experimental versus the theoretical shear strength. And the theoretical shear strength that we're going to calculate is honestly a pretty crude approximation. So it's going to be an empirical formula. It's going to be a constant multiplied by the ultimate tensile strength for that material, and that's going to be the theoretical shear strength. So it's not perfect, right? It's a pretty crude approximation. Okay, and then we're also going to calculate the bearing stress, and then for our plots that we're going to have in the end, it's going to be the shear stress, or really the shear stress versus the crosshead position, and you're going to take note of what the shear strength is, so that maximum shear stress that we have in the test. Alright, so shear stress, it's probably a throwback to the very beginning of your solid mechanics class, right? So it's probably been a while since you've talked about it, but it's a very basic concept. So just like for normal stress, we're talking about the intensity of the force. So for shear stress specifically, it's going to be the intensity of the internal force that we have, and it's going to be acting on a surface, but it's going to be parallel to the internal force. Okay, so for normal stress here on the right, so labs 1 and 2, we have our force on the top and the bottom. So obviously, we're in tension here, and the force, it was perpendicular to this surface, right? So normal stress perpendicular to the surface. Shear stress, it's going to be parallel to the surface of interest. So we have our force going down here in this case, and that force is going to be parallel to this surface right here, or it's it's parallel to that internal force. Okay, and what we're going to see, well, in this case, we're looking at single shear here. So you can imagine that we're applying this force downward, and this is eventually, it's going to fail from that shear force, and it's going to shear off right where we have this labeled in pink here. So it's going to kind of cut right there, and this is going to be that shear surface that we have. So it's failing in this one location. We're going to separate into these 2 different kind of pieces here. So this will be one piece, and then this will be our other piece. So you can kind of think of this like this rod here, that's a rod, and here is kind of like our test fixture, just like we're going to have in the lab. Okay, so that's going to fail. It's going to separate into these two different pieces. And yeah, so it's pretty basic, right? So we have our force going down. That's going to be parallel to this surface here. Okay. So again, this is single shear, and we're going to be doing double shear in the lab instead. So same kind of thing though, right? It's still shear stress, and the only difference is that we're going to fail on these two different surfaces. So I'll draw that out too, just to kind of reiterate what that's going to look like. But before we do that, we'll have our basic formula for shear stress. Just making sure that there's nothing else to talk about before that. Yeah. Okay. So shear stress. So we'll go over that formula. So we're going to write this as tau. That's a terrible tau. Okay, so tau, that's going to be the shear stress, and we're going to have this equal to V divided by A sub V. So I might put either V, I might put F, I might put P. It doesn't matter. Really, that just means that's the load, but by convention, V is usually used for the shear force. And then A sub V, that's our cross-sectional area for this kind of surface here for where shear is going to occur. But it's just the cross-sectional area. Okay, so obviously it's just the force divided by the cross-sectional area, and then we get stress. So this equation, it's very simple, but something to note here, that equation right there is only for a single shear. So we're only looking at, one kind of plane for the cross-sectional area. For our lab, like I've been saying a lot of times now, we're doing double shear, so we actually need to modify this formula. But before we do that, we'll kind of look at what this is going to look like for double shear. Okay, let me go over here. Alright, so for double shear, we're going to have something that looks like this kind of setup. Okay, there we go. So in our lab, it kind of looks like this. Think back to the slides I had in the beginning. So we have a kind of centerpiece. Let's actually pull it up, give more context. Alright, so in the lab, we have this kind of centerpiece, and that's going to be pushing down on our sample. So that's what I have here in this kind of box. That's this centerpiece here. That's going to be pushing down on our rod. And then we're going to have these two different surfaces here where that's going to be the shearing surface. So we have double shear. We're going to fail right here, and we're going to fail right here. All right, so we have those two different surfaces. So here and here. And in the very middle, we're going to have our rod is going to be there. All right, so in the end, it's going to look like this. This is a thicker rod than we have. Yeah, okay, sounds like, yeah, whatever. Okay, so this is what the rod is going to look like in the end. We're going to have this short middle piece here, and then it's going to shear in these two different spots. Alright, so to revise our formula, all we need to do is put a 2 in front of the cross-sectional area, because we're going to be in double shear. Alright, so I'll draw that out again for what our test setup is going to kind of look like, just to reiterate. So we have our rod here. We're going to have this kind of, that's so bad. We're going to have this kind of square piece. It's not even centered. Okay. We're going to have this kind of square piece here where we are applying a load. And then we're going to have these two different surfaces here where that's going to be where we fail from shear. So we'll call that A1, this will be A2. Again, they're going to fail right there. And this is double shear. So to modify our formula for double shear, we have tau is going to be equal to our shear force divided by 2 multiplied by that cross-sectional area. So obviously our rod here, the cross-sectional area is constant, so we can just put a 2 in front of that cross-sectional area that we calculate. We can rewrite this. I mean, it's so basic, I know, but just for simplicity. Okay, so we have our load divided by 2 multiplied by that cross-sectional area, pi divided by 4 multiplied by the diameter squared. Okay, there we go. So very basic formula. And then, so that's going to be the experimental formula that we have for our shear strength. So V here, that's going to be our maximum load. So, we can put V max there. So all you need to do, really, you're going to export the raw data, and just in MATLAB, we're going to use the max function so we can get that maximum load that was on the rod, and then we can get our shear strength that way. Taking that max load divided by 2 multiplied by that cross-sectional area. Okay, so that's the experimental. And now we need the theoretical formulas. So these are empirical formulas. Right, so some tests have been done, and these formulas were developed to kind of give a prediction for what the shear strength is like for these different materials. Again, pretty crude approximations, so keep that in mind. So for copper, so I'm going to write this as tau max for our shear strength. That's going to be 0.65 multiplied by the ultimate tensile strength for that material. And again, I think it's copper C40, so I'll double check that once we actually get to the lab. Just so you know what material to look up when you're finding that published value for the tensile strength. Okay, and then aluminum is the same formula, so it's going to be tau max equals 0.65 multiplied by the ultimate tensile strength. And then for our steel, 4140, right? Was it 4140? No, sorry, 1018. So for 1018 steel, we're going to have tau max equals 0.75 multiplied by the ultimate tensile strength. Okay, there we go. And so we're going to, plug this in, and then we're going to compare that with our experimental shear strength. Sorry, I need to answer a text really quick. Gotta feed my dog. Okay. Alright, so there we go. And now we're going to talk about the bearing stress. So we're calculating the shear stress in this lab. And then we also need to calculate the bearing stress. So I think I closed out of it. Yeah, I should have kept this open. Alright, so in here, if we're looking at this test setup here, remember we're taking the centerpiece and we're going down. And so, we're going to have mostly shear stress that's going on. But we're also going to have some bending stress too. It's, it looks a little similar to the beam lab. Obviously, we don't have a beam. We have a rod here instead. But, there's some bending force that's going on because we're pushing down in the center, and that's going to create some amount of deflection. There's going to be some bending moment going on there. We're not going to calculate that, but just keep that in mind too. So there's shear going on, there's bending going on, and there's bearing stress going on as well. Because, like we said in the beginning of the class, that we have our rod here, and there's this shared area with the rod and these little discs here. So we have a disc here, a disc in the center, and a disc over here. So the rod and these discs, they all share some area, and because of that shared area, we have some bearing stress. Alright, so we're going to calculate that bearing stress as well. I'm going to pull up an old video that I made for a past class. And we're going to look at the cross-sectional kind of view here. So, we have our setup here. We got our rod and our 3 different sections here. And then if we look at a cross-sectional view here, I think I have a top-down view. Okay, so for bearing stress, remember that's when we have 2 different materials or surfaces that share an area. So in this case, it's going to be our rod, and then those 3 different kind of sections, right? So the rod and these 3 sections, they're sharing an area. So in this case, it's starting on this edge right here, and it's ending on this edge over here. So if we look at this, we're going to get the length in this section here. So starting at this edge, going to this edge, we're getting that length, and we're going to multiply that by the diameter of the rod, and that's going to be that kind of shared area. So to calculate the bearing stress, we're going to get the force that we have and divide it by that length multiplied by the diameter of the rod. Okay. Pretty simple, right? Pull this back up. Okay, so we'll call that sigma B for bearing stress. That's going to be our force. So see, now I'm putting F just because we usually use V for the shear force, but it's the same force here. So we have our force divided by, for this lab, the length of the rod. I'm going to put L sub M because it's got something in my eye. It's the length of the rod that's in the middle. So it's the length of the rod with that shared area with with those 3 different discs, okay? So L sub m multiplied by the diameter of the rod. And that's it, right? So we're just going to plug that in. So we can plug this into MATLAB as well. We're just going to get that load divided by the length of the middle, multiplied by the diameter, and that's it. So this length of the middle, remember, that's the length that we're going to measure after the experiment ends. So we'll use our calipers and get that length, put it in the Excel sheet, and that'll be a very simple calculation. So I don't think we have any graphs for the bearing stress here. It's just going to be one kind of result here. All right, so yeah, that's it for the theory. So pretty simple. Looking at the shear strength, looking at the bearing stress, or looking at the shear stress and the bearing stress, and that's it for this lab. So this lab is one of the more simple labs, I think. Well, to be honest, they're all pretty simple for this this class. I've said it to a few people, but the next lab you're gonna take, the fluid mechanics lab, is, I think it's the most intense lab. So enjoy this lab while you can, because it's pretty simple and it's pretty short compared to the fluids lab. Although that lab is pretty interesting too. Alright, so that's it for the theory. So before we end it for today, remember your 5th memo, that's going to be due on the 29th of November. You got to do that data reduction by yourself. Give it a very, honest effort by yourself. So try to go through all of it yourself. Use your own method. Do that first before looking at what I gave you in the deliverables handout, because I don't want to box you into my method. So go about it yourself, and if you're really stuck, then you can look at my kind of recommended guide. But you don't need to use that exact method either, right? Do whatever you think is easiest for yourself. You still need to use MATLAB though. But if you don't want to use a nested for loop, you don't have to. It's the most efficient, or it's one of the more efficient methods. Yeah, also it might be more efficient, but if you can't get it right, you can use whatever method you want to do. And after everyone submits their report, I'll actually make a video too going over what I did. So yeah, if you add me for MATLAB, of course I want you guys to be as efficient as you can with your code, but this isn't really a MATLAB class, so I'm not gonna grade you on the efficiency of your code or anything like that. But you do need to have code for solving for that ductile to brittle transition temperature. So yeah, that's due on the 29th. So remember, next week is the fall recess, so don't get started on that data reduction on the last day. I know a lot of you guys do it on the last day. Just being honest here. That's going to be a terrible idea for this lab, for the 5th lab. If you start it on the last day, you're setting yourself up for failure then. So hopefully you got started now. I know probably, honestly, maybe no one did. But get started on the break, at least get some progress day by day. I don't want you to not enjoy your break, but you've had a long time to work on this 5th lab now. So make sure you get started before that very last date so you can actually complete it. Okay. And yeah, so I guess that's it for the announcements there. If you guys have any questions, you can ask me, once we're down here. But yeah, keep all this stuff in mind. And so next week is the break. A week after that, we have our 6th lab in person. And that's a pretty fast lab as well. So we'll do that. We'll get out of there. You can study for, midterms, or probably still midterms. Study for your midterms, do any projects you gotta do. And then the week after that, we'll talk about the final. And then we'll do the final. Yeah, that's the plan for the rest of the class. Alright, so that's it for today. What? Why is Alexa stop? My Alexa just started playing randomly. Okay, so that's it for today. All right. If you guys got any questions, you can stick around, ask me. But that's it. So I'll see you guys not next week, but the week after. All right. So have a good weekend.
Patrick, I don't want to bug you during the break, but if we have any issues with the lab report, will you be around or no?
Yeah, I'll
Because I
be
get
around.
it if you won't be around.
No, I'll be around. I'm not gonna answer right away, of course, but whenever I have free time, I'll check Discord.
Okay, thank you.
Yeah,
Have a nice break.
you too. Kevin, got any questions?
I don't think so. Um, Thank you very much. Have a
Okay.
good break.
Thanks. You too.
All right, see ya.
See ya.